Picture this. It's 2026. The world as we know it is facing a dark, chaotic reality. A crippling energy crisis has literally paralyzed global infrastructure. But while the headlines are absolutely screaming about grounded airplanes and total economic collapse, there's a mysterious, highly advanced breakthrough quietly unfolding in Shanghai. Our mission for today's explainer? We're investigating this exact technology, the breakthrough that promises to change the very nature of energy and flight forever. To truly grasp the sheer scale of this miracle, we kind of have to understand the nightmare first. By April of 2026, the global aviation industry has basically been brought to its knees. Jet fuel prices have breached a staggering $200 per barrel. Think about that. Airlines are collapsing, inflation is surging out of control, and the fragile fossil fuel supply chains that the world relies on have fundamentally shattered. If we look strictly at the raw geopolitical data, the catalyst for this massive shock was the outbreak of war in Iran in February. The resulting maritime blockade was devastating. I mean, the closure of the Strait of Hormuz effectively choked off 20% of the world's seaborne crude oil and an incredible 25% of all jet fuel exports. The world urgently needs an alternative, and we need it fast.
Just look at this headline for a moment from the South China Morning Post. This is the news behind today's video. Chinese team pioneers path to turn carbon dioxide into jet fuel as prices soar. Scientists use iron-based catalysts to overcome barriers in chemical process, bringing tech closer to industrial reality. With that said, let's go straight to the intro. The algorithm buries channels that show the truth like mine every single day. The only thing that fights back is you. One like, one subscribe, turn on the bell icon. That's how the truth about China survives on YouTube. Don't let it disappear. Thank you very much.
Section 1. Investigating the reverse combustion miracle. Let's dive right into the concept of reverse combustion. We all know how normal combustion works, right? You burn fossil fuels, create energy, and you release CO2 and water as waste. Well, the geniuses over at the Shanghai Advanced Research Institute and the Chinese Academy of Sciences have actually figured out how to run that entire process backwards. By taking waste CO2 directly from the atmosphere and combining it with green hydrogen derived from water, they're reassembling these molecules into energy-dense liquid hydrocarbons. They are literally building a steady stream of jet fuel out of thin air. Well, out of pollution, to be exact. Now, the absolute holy grail of synthetic fuel has always been controlling exactly how those carbon chains grow. And the secret sauce here? It's called the FALK catalyst. It's a revolutionary yet surprisingly inexpensive iron-based catalyst, modified with potassium and aluminum. Here's how it works. During the chemical reaction, a magnetite phase activates the CO2, while iron carbides step in and act like this microscopic precision assembly line, coupling the carbon atoms together perfectly. It's chemical engineering at its finest. And the metrics? They are simply mind-blowing. According to the SARICS research data, when operating at roughly 330 degrees Celsius and just moderate pressure, this chemical miracle achieves a CO2 conversion rate of 38.2%, plus it boasts a jet fuel selectivity of 47.8%. Honestly, these are unprecedented efficiency levels that have completely stunned the chemical engineering world. When you look at the exact output yield, it hits the absolute target. That 47.8% selectivity lands precisely in the C8 to C16 molecular weight bracket. And why does that matter? Because that is the exact range required to make conventional, usable jet fuel. We're not just making useless methane gas here, we're making the real deal. Section 2, the 800-hour marathon. Now, the massive leap from clever lab chemistry to actual industrial factory floor production is proven by one single metric. While most standard catalysts around the world just die out or deactivate after 100, 200 hours, the Chinese team maintained peak performance for a staggering 800 continuous hours. Let that sink in. For over a month, this catalyst ran non-stop without degrading. No way, right? To really appreciate how punishing that 800-hour marathon is, you have to understand why catalysts usually fail in the first place. Typically, they suffer from coke deposition, which is this choking, suffocating carbon buildup. They go through volatile phase transformations where they entirely lose their chemical structure. And they suffer from something called sintering, where intense heat causes the active metal particles to melt into useless clumpy messes. But the researchers bypassed these destructive hurdles with an absolute stroke of genius. The aluminum in that FALK catalyst acts as a physical structural spacer. Think of it kind of like rebar reinforcing concrete under intense pressure. The aluminum prevents the iron nanoparticles from sintering and clumping together, even under the intense 330 degrees Celsius heat of the reactor. It physically protects the crucial chemical interface for the entire duration of the marathon. Section 3. Modular plants and infinite power. Enter a high-tech startup called Feynman Dynamics. These guys are completely shifting away from the old monolithic chemical plants that, let's face it, take decades to build and are incredibly rigid. Instead, they're utilizing these Lego-like modular units. We're talking standardized reaction units that can be factory-built, shipped, and snapped together on site in a matter of weeks. It allows for incredibly rapid linear expansion. It's a total game changer. This architecture supports a highly strategic geopolitical pivot known as the production follows power model. Because these plants are modular, they can be deployed directly at massive wind and solar hubs. This entirely decentralizes fuel production, meaning nations can completely bypass vulnerable maritime choke points like the Strait of Hormuz. Neutrally speaking, it is an absolute masterclass in energy sovereignty. Make no mistake though, this isn't just theoretical whiteboard math. Feynman Dynamics has actually signed an agreement and is currently building a reference plant out on the plains of Inner Mongolia. This facility is slated to produce 3,000 tons of electro-synthesized sustainable aviation fuel annually. The foundation of the future is literally actively being poured right now. Section 4. The Airworthiness Certification Marathon. Of course, before a single drop of the synthetic fuel can legally fly a commercial airliner, it has to face the grueling ASTM D7766 certification marathon. It's very much like clinical trials for a new pharmaceutical drug. This fuel must pass 4 absolute tiers of testing. Step 1 is basic property evaluation, things like density and freeze point. Step 2 requires deep chemical composition analysis. Step 3 is rigorous engine hardware testing. And finally, Step 4, full-scale flight operations. The immediate challenge they're facing right now is overcoming what experts call the aromatic bottleneck. You see, conventional jet engines actually require fuel to have between 8 and 25% aromatics, which physically swell the engine seals and prevent fuel leaks. Because this new CO2-derived fuel currently lacks these aromatics, it falls under an Annex A1 category. That basically means it currently has to be blended up to 50% with conventional fuel. It's definitely a hurdle, but one the industry is absolutely racing to solve. Section 5. Next Steps and Infinite Skies. So what does the roadmap out of this 2026 energy crisis actually look like? Well, very soon we're going to see the official launch of that Inner Mongolia 3,000-ton plant. As these modular, Lego-like units begin to scale up, economies of scale will really kick in. By 2035, Feynman Dynamics projects that the cost of this synthetic fuel will contract to achieve absolute cost parity with traditional fossil fuels at exactly $1,500 per ton. And the environmental benefits? They are simply staggering. By capturing concentrated CO2 streams from massive industrial polluters like steel factories and feeding it straight into these reactors, we're creating a closed carbon loop. The life cycle data reveals emission reductions of over 90% compared to conventional jet fuel. It's incredible. The roadmap for the future of global aviation is clearly set. The immediate next steps we'll be watching for this explainer involve scaling that Inner Mongolia reference plant, relentlessly pushing through the Tier 4 ASTM flight trials, aggressively targeting that $1,500 per ton cost parity by 2035, and rapidly expanding the production follows power model on a global scale. We're quite literally watching the birth of a technology that turns our biggest global problem, greenhouse gases, into a steady stream of infinite power. So I'll leave you with this final provocative thought. Could this production follows power model truly be the final nail in the coffin for our fragile dependency on fossil fuels? Let us know your thoughts in the comments. Thank you for joining me on this deep dive into the unknown. Stay curious, and I'll catch you in the next explainer. Goodbye.